Great. Well, I want to thank first the organizing committee for, of course, the organization and for inviting me. Thank you very much, Karina, Vladimir, and I want to thank to make a special thank to Mauricio, not only because he's like standing there, but I need to say that he has been very supporting for us as young researchers at Cinvestav Querétaro. So thank you very much, Mauricio. And I hope this will continue and hopefully it will increase in the future. Okay, so the main purpose of my presentation is to talk about our latest results on how controlling the light emission, fluorescence emission of a single layer of molybdenum disulfide using what we call a hybrid gap mode metasurface structure. So this presentation will be, I will talk about, we'll change a little bit the dynamics of this, of what we have heard before. I will talk about a little bit of solid states and excitons, and of course metasurface and so on. All right, so 3 years and a half ago, I convinced a bunch of young guys to start working in this 2D material business. Perhaps they were too young to know what kind of deal they were making, but as Vladimir mentioned, we have learned a lot, plumbing, electricity, besides the physics part, right? Of course, this is the slide that I use in every single conference that I go, so, but you know, this is Cinvestav. Cinvestav is the largest institute of Mexico. It has like 8 campuses, and we are here, located here. And of course, if you have time, or if you haven't gone, you may visit Querétaro downtown, so it's a beautiful place to have a drink or a coffee or whatever you like. Okay, so besides plumbing and electricity and so on, we have developed a what we call a nice toolkit of single-layer semiconductors, especially molybdenum-based family. So here, what I'm showing you is an optical image of these crystals laying on silicon dioxide, and here are the excitonic resonance of each one of them. These are like single monolayers, the emission of single monolayers. Okay, so one part of the research is dedicated on growing monolithic two-dimensional semiconductors, but also we have developed a technique to grow what we call a van der Waals heterostructure between them. And we have shown that if you stack, for instance, molybdiselenide on top of, molybdisulfide on top of molybdiselenide, you end up having this two-type heterostructure. And if you pump a little bit, and if you increase also the pumping excitation, there is an interesting phenomenon called like the charge transfer. So electrons coming from this point will immediately transfer to the MS2 materials, forming not only excitons, but a three-body particle core called trion, or what it is, a charge excitons. So besides the growth of these to the semiconductors, we are also working towards some applications. So in this sense, in collaboration with Edgar Serga at el Instituto de Investigación en Comunicaciones Ópticas, we have managed to insert these 2D materials in a TBR microcavity based on porous silicon, right? In order to match the photoluminescence emission of a single layer of, I think it's tungsten disulfide, to the absorption of this cavity, right? And this is the results of measuring the decay space with that plus the cavity, and the cavity plus the materials. And it is not the very convincing results for the polaritonic community, but we want to see, well, with a little bit of imagination, you can see, or we want to see, the operation of the upper and the lower polaritonic branches. I have to say, in our defense, that this image was taken with a $50 refurbished CCD camera, so there's a lot of improvement in this kind of applications. And today, what I will talk about is an optoelectronic application using a single layer of molybdenum. So let me start with some motivations. So during the last 10 to 15 years, the nanophotonic community has put a lot of effort to develop a new kind of devices called metasurfaces. And one of the reasons is that you can actually replace the optical bulky components by patterning the surface of a material. So if you do that in a very smart way, you can actually design the waveform of the transmitted light. So you can play with different features of the transmitted light, so you can focus the light, you can play with the polarization, you can play with the phase, right? Within the same device, right? On the other hand, you have this new family of materials called transitional metal dicalcohenides. Unlike graphene, as I showed you, these are true semiconductors with well-defined band gaps. Okay, so they can cover a large spectral range going from 1 to 2.5 electron volts. And I think that the easiest way to imagine what is a monolayer of these transitional metal dicalcohenides is to make like the analogy of a sandwich, right? So you have a bread slice, right? Two bread slices representing dicalcohen atoms, and in between you can have ham or cheese, whatever your preference is, right? So this represents a monolayer of these materials. Actually, one of the strangest things of these materials is that if you take a look to the electronic structure, right, they present a large split orbiting coupling in the valence bands and in the conduction bands. So between these two quasi-equivalent values, they are spin locked, right? So the transition. So these open a new set of transition rules, exciton transition rules. So you can have polarization, right hand, left hand polarizations, but also there are exciting opportunities here because there are also forbidden transitions between them, what is called dark excitons. Okay. Besides that, of course, because they are so thin, so this is like about a 6 angstrom thickness. They present strong confinement and make these materials suitable for ultralight and low power consumption devices, such as electronics, since you can choose to populate one or the K or the K prime valley. Single photon emitters, where I'm looking forward to collaborate with Neil. And of course, because since they are soft wavelength dimensions, they are perfect for metasurface integration. So in this sense, people have already started working. So this group demonstrated that taking a sheet of tungsten disulfide, and because they present also large susceptibility, they managed to focus the second harmonic generation of these materials to focus up to 100 microns. So it's not a lot, but I mean, again, it's a proof of concept. So as I mentioned before, you can attain this strong coupling regime. For instance, if you insert this kind of structures, which is like again a sandwich between to the materials, and if you insert it in these like fancy optical cavities, right, you end up having this beautiful anti-crossing PL dispersion, right? Another kind of I mean, again, this is like a photon-exciton coupling, but you can also have a plasmon exciton coupling if you put like plasmonic arrays in this transistor made of molybdenum, and if you change the bias, you start like the polaritic branches start to appearing. However, one of the drawbacks of these materials is the amount of light absorption, right? Because they are so thin, they cannot absorb a lot of light. One way to overcome to this problem is to enhance the light-matter interaction by confining the electric field near to the material. For instance, you can this group showed that it is possible to put like bow tie antennas on top of this crystal, and they show that the luminescence grows up like for I don't know, 2.3 orders of magnitude. You can also make holes, an array of holes, and again increase the electric field near to the material, so the luminescence grow. And also another trick is that if you put like a mirror laying below the 2D material, you have like a Fabry-Perot cavity that will enhance the absorption. So we wanted to put these three ingredients, metal surfaces, 2D materials, and a way to enhance the light emission into a single device. So we came with this design or this idea to put a mirror, a gold mirror, first just deposit on silicon dioxide, then put a spacer, right, a silicon dioxide spacer, then the 2D material, and finally the metal surfaces. So if you take a careful look, you will see that the mirror will also support this SPR resonance, and of course there's a Fabry-Perot, and more importantly we will have electrically access to the monolayers. Okay, so how we grow this to the material? So actually it works like magic. You just have to put some temperature powders, and if you tweak a little bit the parameters, you end up having these crystals, right? And again, these crystals are like 6 Armstrong thick, so very basic idea, and I'm still amazed that you can get these results. So what I'm showing here is the photoluminescence, the photoluminescence emission of almost 2 layers laying as drawn laying on SiO2, and you can see that if you decompose the spectrum, you have 3 components: the exciton A, the trion, again the charge exciton, and the exciton B. However, when we took these materials and put it on top of the structure, the gold mirror, we found out this. So these 2 spectra are perfectly comparable because they were taken at the same time, almost at the same time, and you can see that there is this PL enhancement due to the multiple refraction in the Fabry-Perot cavity. But also, you will see that the exciton A will blue shift, right? And this is because we are entering in this plasmon exciton coupling. Okay, so based on this information, normally people don't want to have like a broad spectrum, but what we did is to take advantage of this broadening to sort of design a cavity to match just the exciton A resonance. So we decided to integrate like a metallic nanostrips array where each of these stripes can be seen as a Fabry-Perot plasmonic cavity, right? So we run some simulations in order to design these cavities. So this is the reflectance of this resonator, and this is the electric distribution of this resonator also. It is important to mention that, of course, due to the nature of these metallic nanostripes, you will have control about the polarization of the light emission. So we went to clean rooms to fabricate our device. So this is like 1.5 to 1.5 centimeters, and we combine optical and electron beam lithography to put these nanostripes on top of the crystals. So the width of each nanostripe is about 72 nanometers, and the periodicity is about 350 nanometers. So we match the simulation conditions. So after that, we measure the photoluminescence in this point and in this point, and even in this crystal, which is like in the boundary between the two, without this rating and with rating and without rating, and we found this, right? So we have what we wanted. We enhanced the PL emission, right? But most nicely, we demonstrated that that we have control on the polarization of the emission. So the TM component is like 4 times larger than the TE component. All right, so since we have electrical access to the monolayer, we asked ourselves if it was possible to manipulate in real time this interaction between the cavity and the excitonic resonance presence in the MOS2. And so let me try to explain how it works. So this is the PL emission at 0 bias. But then, if you apply or inject, I think in this case, let me see. Yes, if you inject electrons to the MOS2, you will promote the generation, or you will promote the population of trions. And this will detune completely the plasmonic optical cavity, right? However, if you change the bias, so inject holes, you will decrease the population of trions, and you will tune nicely, and you will enhance again the emission of the PL emission coming from the single layer of MOS2. So I will finally want to thank all the guys that participated in this work, also the money guys, and especially I want to thank Andrés de Luna B that hosted us for I think 6 months in his lab at Crea in France. So finally, of course, I want to thank you for your attention.
We have time for several questions. In your last plot, can you go back?
Sure.
So you put -30 volts. Is there, well, 2 limits? How much voltage can you put?
Right.
And do you expect to keep going up, or at some point you're going to stop?
Right. So yes, of course, the electrical part, it depends on how good your dielectric is before it breaks down, right? So 30 volts, I think 30 volts is a lot. So one way to improve this is by putting like these high K dielectrics. Just you need a good dielectric to go up, and to see like more to increase the effect, to increase the constraint. Yes.
Any other question? Okay, if there are no more questions, let's thank the speaker again.